So thanks a lot for all of you being here, and special thanks to the organizers for bringing me in this wonderful place that is one of my favorite schools. It's always great to be here to do science in the water, which is even better. So after my talk, I will be swimming, so whoever wants to come and discuss, I will be in the water. And a special thank is for the organizers for setting me as a first speaker. First, because it's a big honor, but even more because then I will be free to discuss in the water. So today I'm going to present, some overview about quantum fluids of light with a few other topics connected, which are, in my opinion, especially interesting and prone to exciting developments. So to get started, anyway, a few words on the idea of quantum fluid of light in order. So for those who are not in the field, basically the general idea is to start a new investigation of many-body physics of systems where the fundamental constituent is not a material particle, but it's a photon. So this may seem quite bizarre, because photons, say, in vacuum don't interact, they just fly through space at speed c. But the key idea of this field was that in suitable systems, one can make the photons to interact with each other and to display an effective mass. In this way, having a mass and interactions, one can force assemblies of photons, like one has in a beam of light, to show a collective behavior like the one of a fluid of interacting particles, like water or like air. In this way, the original expectation was to find new regimes of hydrodynamic physics in a completely new setting with possibly very new properties. So, photon-photon interactions were one of the key problems. We know, normally we are taught in second year undergrad that light field is described by Maxwell's equations. Maxwell's equations in vacuum are linear, so one would expect that photons do not interact with each other. Basically, light beams can cross each other with no effect one on another. Actually, this is not true at the level of QED, because processes where photons collide exchanging virtual electron-positron pairs exist already at the level of QED. They were discovered by Heisenberg and Euler in the 30s. The problem is that these phenomena, involving very massive intermediate states of the order of megaelectron volts, these are very difficult to be observed. They are very much suppressed. And indeed, if one calculates the cross-section for this photon-photon scattering, the result is a very small number. There are 4 alphas for the 4 vertices, some Compton wavelength, which sets a characteristic length scale, and there is this very nasty factor, which is the energy of the photons over the mass of the electrons to the power 6. Since this laser has more or less 1 or 2 electron volts of energy per photon, and the electron mass is of the order of 1 mega electron volt, this is a killer factor of 10 to the minus 36. And this is why the first evidence of these photon-photon processes has come only very recently at an experiment at Atlas at CERN, this Nature Physics paper, which is a kind of indirect evidence. But looking at this formula, it also tells us that this phenomena can be observed in practice if one replaces the intermediate electron-positron pairs by electron-hole pairs, for instance, in a solid. In this way, this factor 10 to the minus 36 goes to 1, because a solid, typically the gap is 1 electron volt. One gains a factor 10 to the 36, which indeed brings this very difficult physics to be observed to something which is actually can be observed. And actually it's observed almost every day in any nonlinear optics lab. Because this photon-photon collision process in nonlinear optics correspond to a local Chi3 nonlinearity, which is something that we learn in basic classical optics course. Of course, this idea of exchange of electron holes is a very naive. There are many materials in reality which are used for nonlinear optics, which are much better. They involve more complicated optical transitions. And in particular, I can mention Rydberg atoms. So EIT with Rydberg atomic states is used to get very strong photon-photon interactions, or also interactions mediated by superconducting devices, where a macroscopic number of electrons behave in a coherent way in a Josephson junction, displaying very strong optical nonlinearities. So this is just the idea that some concept, which is kind of very abstract, can become something completely common in experiments, can be even pushed towards the regime which is completely opposite to Maxwell, where the photons are so interacting that they're like billiard balls. They just bounce on each other, like a rigid object. They are impenetrable objects. So one goes from non-interacting photons at Maxwell to billiard balls in this exceptional media. So to give photons in a mass, there are several strategies. We will see during this event experiments doing different strategies. The first one on which I've been working is to use a planar cavity. Basically, you take two plane parallel mirrors. In this way, the electromagnetic field has to display nodes at the metallic mirrors, so the motion along Z is quantized. And the effective dispersion for photons traveling along the plane is shown here. It has the form of a relativistic dispersion, exactly the one that one finds in relativity for particles of a mass, which is in our case set by kz squared, so the confinement along this direction. So basically, just confining photons between two mirrors, you make them massive. Here, dispersion, you see these are the different branches corresponding to the number of nodes along Z. Typically, experiments are done with the lowest branch, which displays an energy gap, which is a sort of rest mass, and the curvature along the bottom, which is the usual kinetic mass. So if your experiment contains photons which live in this bottom part, they have no relativistic massive dispersion. Combined with the interactions we have seen in the previous slide, we get an ensemble of interacting massive particles, which is exactly what one needs to do many-body physics. Of course, there is a detail, but being in a cavity, photons typically, they don't live forever. If you do an experiment with cold atoms, you can load the trap, go out for a very quick coffee, you come back, you have a chance of finding again some atoms, more or less. Here, you have to take a very quick coffee, which lasts 1 nanosecond at most. So it's very difficult to bring the system to a sort of thermodynamical equilibrium, because you don't have the time. At the beginning, people were extremely worried by this. There are tons of papers about how to make photons to get to thermodynamical equilibrium. But as usual, one can turn a bug into a feature. One forgets the idea of getting the system to thermodynamical equilibrium, which actually is not interesting, because it would repeat something that can be done much better with cold atoms, and rather allows to go to new regimes of systems which are intrinsically non-equilibrium systems, non-equilibrium many-body physics. In this way, one can take advantage of the fact that you need to pump, to use the pump as a way to force the photons into some many-body state that you like most. So you can tune coherent lasers, you can use incoherent pumps, you can even engineer exotic non-Markovian pumps. All these can bring the system towards different many-body states that can be exploited. One further very important point is that the light which is emitted by the cavity just via the transmission through the mirror gives you an exact copy of what's happening in the cavity. In this way, just by looking at the light emitted from the cavity, you have a real-time in situ imaging of what's happening to the many-body fluid, which, if you compare to what happens in cold atoms, where typical measurements are destructive, it's a great advantage, a great experimental advantage. Even more, if you think that the experiment lasts 1 nanosecond, so imagine what repetition rate you can have to accumulate statistics. So you can really accumulate massive amounts of data to make experiments very precise. And this is what is being exploited in experiments. The typical description at the level of weak interaction fluids is a sort of Gross-Pitarski equation, where one recognizes easily the effect of pumping, which is in these terms which are plotted here in color. This would be an incoherent pump, this would be losses, this would be an incoherent pump. So the basic structure of the motion equation for a gas of photons, weakly interacting photons in a cavity device, is a Gross-Pitarski equation plus some new terms describing driving and dissipation. There is an artillery to study these systems. There's been all the ones in cold gases, but there is also a big artillery of methods which were developed much earlier than all these existed. So the idea of treating the photon fluid as a gas is one angle onto this physics. But at the same time is the equivalent angle of attacking these problems from the language of nonlinear optics. So the two words seem completely distant, but they basically are just different angles on the same physics. So one thing that I really urge you to do is to have a look at the immense literature which exists in other fields, which can be used to shine light on these ideas from a completely different angles. For instance, I like very much these lecture notes of Gigi Lugiato, that I actually first met at a conference here in Cargèse around 20 years ago. I came here to learn about the nonlinear optics physics of these cavity devices, which gave a set of lectures on these kind of systems, where the generalized Gross-Pitarski equation that I showed you here exists, is studied very much. Here is this typical form. It takes the name of Lugiato-Lefebvre equation. So if you have a problem in a system that you think to be new, just have a look at what happened 20, 30, 40 years before, because you may find some interesting insight in previous works. So we are the small Masha, and we are sitting on a big bear. So we have to rely on the shoulders of the big bear, and we have also to pay attention that sometimes these old gurus may get angry and do what Polifemo does here to Ulysses, throw a rock at you because they can get very angry. So this is a kind of a general suggestion, and it's something that you find incredibly interesting insight in these old works. Good. So during this conference, we will not only see these cavity geometries, there will be also several speakers speaking about this other way to generate quantum fluids of light, which historically was actually even a bit earlier, and is based on a reformulation of light propagation through a nonlinear medium in terms of a conservative Gross-Pitarski equation, which is typically written for monochromatic light, where it takes this simple form, and where the mass comes from diffraction on the transverse plane. This is just paraxial propagation, which gives a lot of physics which can be understood in terms of hydrodynamics. There are anyway a few things one has to really to keep in mind which make the difference between these two cases. Here propagation is a fully conservative problem. So the incident beam sets the initial condition at z equals 0, and then the evolution is fully Hamiltonian, is a conservative equation, to be contrasted to the driven dissipative Gross-Pitarski that we saw for the cavity configuration. So this makes the dynamics completely different, and in a sense, if one wants to look at subtle quantum correlations, this system has a strong advantage of being conservative. Another thing is that that equation that I just wrote is for monochromatic light. But we know that any beam will not be exactly monochromatic. It will have some time dependence, a bit of time dependence. In that context, one has to improve, so extend the equation by including also the physical time, and one gets an equation which is the same form, just including another term describing the dispersion of light, so chromatic dispersion during propagation. In this way, we recognize that this is a three-dimensional GP. It's no longer 2D, it's 3D, two spatial dimensions, and physical time plays the role of a third spatial coordinate, while the propagation direction becomes the time of evolution. So there is a sort of a TZ mapping, where time becomes an extra spatial variable, and the propagation direction becomes a temporal variable. So this idea was fully developed by the man who's sitting in the back, Pierre Elie, in this old paper when he was a postdoc with us in Trento, and even realized the even more subtle point, which is how to quantize this theory, bringing the classical mean field theory towards a really quantum fluid. Because if you think of the monochromatic description, those photons are extended in the whole time from minus infinity to plus infinity. So the idea of corpuscular photon is not present in a description of a monochromatic light. If insert time, then the description in terms of photons come out completely naturally, just keeping in mind that the TZ mapping has also to be included at the level of the commutators of the theory, where since Z plays the role of an effective time, one has to impose a canonical commutation, not at the same time at different positions, but at the same Z at different times. And this is what one can show. So the mathematics before leading to this equation can be a bit complicated, but the final result is very simple. One describes the quantum evolution corresponding to this propagation in terms of this Hamiltonian, which is standard Bose-Gas Hamiltonian, where the Z and T play different roles, so the integration of the Hamiltonian is here has to be put over time. This is a very convenient picture. It allows to make calculations quite easily, and we will see in the talk by Alberto, it's on Thursday, how these ideas can be exploited to generate, for instance, strongly correlated gases of photons in propagation geometry. And so this idea, you will see from Alberto's talk, is something that can be pushed to experiments. And indeed, we are setting up a machine in Trento, together with Federica, to use microwaves in superconducting waveguides, which is an alternative platform where to study interacting photons, propagating geometry, exploiting all the technology that has been developed over the years to build superconducting amplifiers, the so-called traveling wave parametric amplifiers, TUPAs, which is one of the most used devices for quantum optics in the microwaves. There are companies selling these devices for even particle physics applications. An interesting thing is that this kind of configuration are compatible with proposals for synthetic gauge fields, for synthetic magnetism with light. So they could, on the long run, even go towards more complicated states of matter, such as fractional quantum Hall. Very good. So it's time to move on to the first topic of, contemporary research I would like just to address, which is the idea of non-equilibrium condensation and their links to lasing, and a few questions which have originated from this research and are still waiting for an answer. If you want to have a general idea on this topic, you can look at this review paper, where I have to just make a caveat. The general ideology which is contained in this paper is my very personal point of view, shared with Jacqueline and Michel. Not everybody agrees with this picture. Just have a look and make your own opinion. I'm trying to be as honest as possible without overclaims, because often in this community there have been overclaims to publish in Nature rather than on PRB. And this is, my opinion, often very misleading for the general scientific purpose. So in this review, we try to clean up all the field from all those overclaims. Good. So this adventure in planar cavities culminated with this 2006 paper by the Lausanne group, which was building up with some slightly earlier results in Grenoble by Max Richard. Basically, together, the two teams culminated in the first experimental characterization of condensation in terms of the appearance of a very sharp peak in the momentum space distribution, and at the same time appearance of interference fringes between two condensates. And these are the smoking guns of condensation. Of course, being a non-equilibrium system, you cannot tune easily the temperature. They were tuning rather the density. Pumping the system harder, or injecting more particles. At some point, these particles were condensing in a very sharp peak at k equals 0. There are these features look very similar to the ones of atomic condensates. There are several differences. I have no time to enter into them, very interesting differences, which are a signature of non-equilibrium physics. These are experiments which were done in cavity configurations, but there are very interesting developments done in thermalization on propagating geometries. So I don't know if somebody will speak about those. This is something which is now in the oven, interesting results, and hopefully in a few weeks or months, something will be available. So it's a very important field also in propagating geometries with the goal of doing some beam cleaning. Good. But looking at this condensation stuff, you should immediately jump on the chair. Because there is a theorem that tells you that condensation is not possible in reduced dimensions. Planar devices are at most 2D. And you know from Hornberg-Mermin theorem that condensation in 2D is not possible. It's destabilized by long distance fluctuations. So long-range physics killed condensation, giving a quasi-condensate rather than a condensate. So a big question was to understand if this was the case also at non-equilibrium, because Hornberg-Mermin is a theorem which holds at equilibrium. Here is non-equilibrium, and things may be different. In 1D, actually the things are almost identical. In both cases, there is an exponential decay of the coherence. So you cannot have a system which lasers in a coherent way in an infinite one-dimensional geometry. At long distances, the coherence will always be spoiled by fluctuations, which will be either thermal or even zero-point fluctuations. The system will be killed in coherence. And actually, this is a very interesting example of something which had been discovered very long ago, which basically got forgotten. It's a wonderful paper by Robert Graham and Hermann Haken, who pointed out this feature for 1D systems as early as in the 70s. The community in condensed matter know nothing about this paper, and in the optical one it got a bit forgotten also, until in the last year it was so found more or less by chance and got again to the attention. In 2D instead, things are even more complicated. It's not completely clear how the physics behaves. in the sense that there is a competition of several effects. So the BKT transition, which is typically in the cartoonish picture driven by vortices, has to interact with the KPZ physics due to the interaction between the Bogoliubov modes. So there is a debate in the literature what will happen. As far as I know, at the moment, the BKT transition should not be there, should be replaced by some KPZ physics, but I think Sylvain knows more updated information on this. But experiments, final experiments are not available yet, as far as I know. The problem is that to really make the distinction, you need to go to very large sizes of the system, which typically is difficult because then you start having other problems. And this difference was basically understood in a series of papers. And I forgot to mention here the paper by Michel, who actually got to this idea finding a mistake in one of my calculations. We did the things a bit too fast. We used the Bogoliubov theory, but we didn't realize at the time that Bogoliubov theory, in that exact specific case, was not reliable. So Michel did it, found some inconsistency, and realized that this KPZ physics was entering into the game. Too bad for me, I missed the chance of doing some great paper, but Michel did so. Together, of course, with these other people, more or less, at the same time. So for this, in the 1D case, has been a wonderful experiment, C2N. In a 1D geometry, it was an array geometry, but this does not really matter at this level. They measured the space-time coherence function, and they found that coherence is not extended over the whole system. However well you were doing the experiment, there were fluctuations, 0-point fluctuations, destroying the coherence at long distance. This is a coherence map, position, time, and even at the same time, coherence drops at long distances because of the non-equilibrium Hohenberg-Mermin-Wagner theorem. Going at finite times, things get even more interesting because there is a universality behavior. So, welcome. So there is interesting features that the cuts of this coherence function collapse onto universal curves, which are described by the Kardar-Parisi-Young universal curve. Kardar is Meran Kardar, is a famous statistical mechanics person. Giorgio Parisi is Giorgio Parigi. I don't know about Young, who he is, but perhaps he's a very good scientist as well. Zhang spirit is taking his revenge. So Zhang is a wonderful physicist, even better than C.N. Yang. Very good, okay. Thanks, Claire. So they fall into this universal curve. So these experiments showed that the physics of these 1D condensates is dominated by KPZ features. But if you turn the idea around, this also tells us that making a laser bigger and bigger and bigger, at some point it will hit against a hard wall for what concerns the maximum coherence you can achieve. So there is no free meal in physics. People have been investing a lot of efforts in building lasers bigger and bigger and bigger to have a larger intensity while keeping perfect coherence. These work well with the limitation of this KPZ physics, which tells you that at some point the system will lose its coherence because of fluctuations. And these fluctuations are ruled by these universality curves. The basic mechanism why this is a KPZ is not other universality class is because of the interactions between the Bogoliubov excitations in the system. So natural question is to understand what are the ultimate limits you can get, for instance, to the coherence of this source used as a laser. We know from basic laser theory that in a single mode approximation, one has a phase diffusion which sets the ultimate limit for the coherence to the Charlotte-Towns line width, where the line width decreases 1 over the number of photons in the system. And this is understood at the level of textbooks as a competition between stimulated emission, which goes as n, and spontaneous emission, which goes as 1. So since spontaneously emitted photons have a random phase, they give rise to a phase diffusion of the emission, with a time which scales as 1 over n. This is a bit cartoonish picture, but gets to the point. If you extend this theory to spatially extended devices, you have many modes which are available for the fluctuation dynamics. But as long as the system is not so big that the modes start interacting via the KPZ mechanism, the line width will still decrease as 1 over n. At some point, however, the system gets so large that you start having available modes at very long wavelength, very low frequencies, where fluctuations are larger and larger. So fluctuations are generally larger in longer wavelength modes. Like the population in, say, standard Bose gas, the population of small k modes grows as 1 over k. So those modes are more populated. At some point, you start having available modes where the population is so large that the nonlinear term in the KPZ equation starts being important. And at this point, the modes start interacting with each other. So the derivation, which is behind the Charlotte-Towns formula, starts failing. Something new happens. And this was calculated by this very brave young scientist, Ivan Amelio, who now is looking for a position, who discovered that for a relatively small size of the system, the line width goes up, they say the coherence time goes up as L. At some point, there is some interesting physics not fully understood, and then the trend goes to another power, which is root of the size. And this root of the size is the signature of Kardar-Parisi-Zhang universality on the laser line width. So this is a very abstract theory of statistical mechanics, which was originally invented by Giorgio Parisi and his friends to study the growth of crystalline surfaces, turns in a prediction for the ultimate limitations of the coherence of a laser device. This is a kind of wonderful connection between very abstract StatMech and a very applied problem. So just a general lesson that if you want to find some new things, don't hesitate trying to connect things which are extremely separated, because often there are very hidden connections. And this is an example. Good. Very recently, in the cold atom community has been crazy about the idea of supersolids. So my group in Trento is very active on supersolids. So I've been really influenced a lot by the discussions which were going on around me about these supersolid systems. Basically, an atomic supersolid is a condensate where there is not only contact interactions between the particles, but there are some additional interactions. Could be, in some cases, could be long-range interactions, or could be something else, which basically tend to destabilize a mode at a finite k. So this is a uniform superfluid where this additional interaction has a moderate intensity, and one sees that the dispersion is not the usual Bogoliubov, which goes up straight, but here it develops this Roton minimum, which is observed in this experiment. So what happens if this additional interaction becomes very strong, to go below zero? Basically, the system transits to another state where this wave vector becomes a real modulation in the density of the fluid. So one gets into a state which is so-called supersolid. It's something which preserves phase coherence at long distance, but at the same time it has a spatial order in the density. So it's a system which breaks simultaneously two symmetries, two continuous symmetries. One due to the phase of the emission, one due to the spatial order. What is the smoking gun of all this physics? Is the appearance of two Goldstone modes instead of a single one. One associated to the phase order, one associated to the spatial density order. This is a measurement in the group of Giovanni Modugno in Pisa about the dispersion of the two modes. So, what about doing this physics in lasers? We were very proud of having this great idea, but it turned out that the gurus have already thought along these lines. And there are several papers, again by Gigi Lugiato, but together also with Federico Capasso and Jérôme Feist, so really the big shots in this world of physics, having developed this physics in the optical context. So, in the language of optics, basically the idea is that one has a laser emission, which normally is a continuous wave beam, which gets modulated either in space or time, or in both, by some spontaneous mechanism. Here is an example of this physics, which is in Jérôme Feist's group, where one gets a ring quantum cascade laser to emit in a time periodic way, a sequence of pulses. If you think in terms of atoms, this is very similar to a supersolid device. You have phase coherence in the laser emission, and at the same time you have breaking of translational symmetry, so giving the pulses. So this looks very much like a supersolid. Another very clean experiment which has observed this physics was done with politons using a photonic crystal waveguide. This is of the family of the cavity experiments, just with a bit more complicated device, where at moderate power condensation occurs at the top of this band, at this point. Standard condensation, long range order. But if one crosses some value of the power, there is a secondary instability where politons at this point scatter into this mode -1 and +1. Who have a wave vector difference from 0. This gives a spatial interference, which gives the spatial modulation of the intensity. So, and this corresponds to this second threshold in the emission. So this is an example of system which again breaks two symmetries at a time. In optics, you can understand this as a secondary parametric instability. Actually, it is a secondary parametric instability in the language of lasers, but you can also think of, in the atomic case, the supersolidity as originating to a parametric process which tends to occupy two Bogoliubov modes. So this is another language that you can apply also to the atomic case. In the atomic case, it's not the most convenient way because you are in an equilibrium regime. So the idea of parametric scattering is more something which is common in the language of non-equilibrium systems. But the basic mechanism is exactly the same. You have particles in the condensate which, for some reason, typically related to interactions in both cases, they tend to go into finite momentum states, which are selected by some energy conservation condition, which sets the periodicity of this process. In particular, the periodicity is more or less fixed, but there is nothing which tells you where the fringes have to appear. So the position of the fringes is completely random. It's a spontaneous symmetry breaking. Catherine?
Iacopo, you're saying that the periodicity is kind of it's not universal. It depends on the mechanism, on the specific mechanism of each system, and even the selection of the wave vectors depends on the mechanism of the system.
In a sense, typically here the system tends to go in the window of states which are more or less energy conserving. But you have nothing which tells you it has to be 1 micron minus 1 and not 1.1. So this is dynamically chosen. Also in the atomic case, you see the point where this guy goes through 0, more or less tells you where it goes. But if you say, for some reason, you force the system to have a larger periodicity, then it will slowly go back to the good periodicity. It can oscillate. And this indeed corresponds to the second Goldstone mode, which corresponds to the crystalline-like excitations in this supersolid. Like in a standard crystal, you have excitations of the crystal which move the atoms, making them more compressed, so a shorter periodicity and a wider periodicity in other areas. This is one of the two Goldstone modes. Please.
About the emergence of the order, is this more a continuous transition or is it the first order one?
In this specific case, I don't know. It can be typically second order, but there are cases where it could be also first order. Since the system is at equilibrium, it can do basically whatever you want, because it basically merges with optical bistability phenomena. So you can get that. Here in the atoms, I think it's second order, if I remember well. Good. It's
And where is the super in the super solidity in that case?
the super is basically the coherence of the condensate.
So for instance, superfluid, like in the original experiments, they showed that you can go through a defect and
Yes. Yeah.
perforless.
That's because historically in the atomic world, or like in the liquid helium world, it's easier to measure, say in the helium world, it was easier to measure superfluidity than condensation. So super solid is called super because it is superfluid. And all this business started from liquid helium world, where people were trying to see liquid helium having at the same time superfluid properties and spatial crystalline order. But that's historically. So in reality, also in the atoms, superfluidity is there. There's been nice Josephson experiments by Giovanni. But the reality that you see super solid, what is equivalent to solid is not superfluidity, is a condensation. It should be called consolid rather than super solid. But historically, that's a name which has been established. But what one shows is not superfluidity and solidity, which actually is not the transition. What characterizes the transition is condensation and solidity. Then the question whether this is superfluid or not, that's another question. And this is not clear, I have no idea. Some properties are there of superfluidity, in the sense if you do the quantization of circulation in a ring geometry, this is of course there. There's no problem. But about the defect, that's not clear. And we, together with Giovanni, that many of know in Lecce, we are trying to characterize what are the elementary excitations of this system. We very much expect that it will be dispersive plateaus, but we have not a final result yet. This is an important question. And another natural question is to see what is the effect of this spatial dispersion on, for instance, the coherence properties of this system. How the effect of being also solid affects the coherence properties of this condensate. Is there anything new that happens? That's not known. There are very complicated theoretical papers that suggest that having several symmetries broken at the same time could give some interesting consequences, but it's something that still needs to be studied in detail. Very good. So far, I spoke about up to 2D systems. But, of course, I cannot have a four-dimensional bottle of helium. That's a bit hard. But you can use the idea of synthetic dimensions to build systems with high dimensionality. So you can, if you're tired of living in a 3D world, either you go to energies which are for string theory, and then you have 11 dimensions at your disposal, but you also have to work with algebraic geometry to survive, which is kind of challenging. Or you use this idea of synthetic dimensions, where you try to exploit some internal degrees of freedom of your system as extra spatial dimensions. This has been done in atoms in many different flavors, and in photons is one of the most active fields of developments of current day photonics. So the idea, as we put it forward in this paper together with Tomoki and Hannah, is to use the different modes of a ring resonator, which is very simple ring, where the angular momentum of the photon around the ring is quantized, and this quantum number can be used in an extra dimension. So if you have a 3D lattice of these rings, you have as coordinates x, y, z, the positions, plus the mode index, which is a fourth dimension. So you have an effectively four-dimensional system. Tunneling in real space gives the usual motion along the 3D space. Tunneling along the synthetic dimension can be induced, for instance, by modulating the properties of the ring at the frequency, which is the difference between neighboring modes in the synthetic space. For instance, putting an electro-optical element in the ring and driving it at the frequency difference. Something that experimentalists can do very well. In this way, by controlling the phase at which this extra hopping happens, you can build not only a 4D system, but also a 4D system with a Peierls phase in the hopping between neighboring sites, which is a way to encode a synthetic magnetic field. So a Peierls phase in the hopping is basically like a vector potential on that link. If you build this in a way to have a non-trivial circulation around space, you have built a synthetic magnetic field for photons. Basically, the photons behave as charged particles, which in 1D, nothing interesting, in 2D, Harper-Hofstetter model, in 4D, gets very complicated new physics, because magnetism in 4D completely changes. It has more degrees of freedom. So this idea, this is a very general picture, has been put into practice in a number of experiments. I will concentrate on the ones that I know better, because I've been either involved or I know from close. There are a few others that you find in the literature. So, but say 1D. 1D lattice, you want to have a one-dimensional lattice in synthetic dimension. You don't need to build any special array of cavities. You just take a single cavity, a ring, a loop of optical fiber makes the job. You place electro-optical modulator, you have a one-dimensional system. Here, the group of Philippe Saint-Jean in Montreal wanted to do something more, which is to build a SSH lattice, which is basically the lattice where each unit cell is formed by two sites with alternate hoppings. You see here, strong hopping, weak, strong, weak, strong, weak, and so on and so forth. So it's a lattice which has two sites on each unit cell. This is a phase diagram of the model, where not only the next neighbor interactions are present, not only first neighbor interactions are present, also some longer distance ones. And in this way, they characterized the band dispersion of the model for different values of the parameters, showing, for instance, that these two configurations, which were basically, they differ by some value of some hopping terms. There are different points in this phase diagram. Very similar dispersion, but different topology, in the sense that the winding number, which is a topological index characterizing the bands, has a value 0 in this case. Basically, the wave function is characterized by a loop here, while in this other case, the wave function does a loop which encircles the origin. And the topological index is basically the number of times the wave function goes around the center. This is something that cannot be changed without closing the gap. So it's a topological index which characterizes this lattice. So this was a very fun paper. It was a way to characterize and understand how the machine was working. But it's more of the family of zoology. So we realize something, and we characterize that something has been realized. Where the new physics starts appearing is when one goes to 2 dimensions. In this case, the topology gives rise to a number of very interesting new effects. So the simplest 2-dimensional model is the Harper-Hofstadter object, which displays a bulk topological invariant, is the so-called Chern number, which is an integer-valued quantity which tells us if the system is in a trivial state or in a non-trivial state. Is connected to the magnetic ordering. Typically, in the presence of an external magnetic field, the bands display these topological properties. And one of the smoking guns of this non-trivial Chern number is the appearance of integer quantum Hall effects. So in the early TKNN paper, the integer quantum Hall effect was explained in terms of a non-vanishing number of this index characterizing the photonic bands in the device. In Oliver's talk on Friday, you will learn how this topological object affects some solitonic features of this model. So you create solitons, which are a well-known object for nonlinear optics. You create them in a topological setup, and the fact of having a Chern number non-zero gives new features on the solitonic motion. Of course, by the bulk boundary correspondence, having non-trivial topological number in the bulk corresponds to the presence of having chiral edge states on the edges. And when I mean chiral, these are modes where if this bench is a photonic bench, light in the bulk has the usual band states, but in the gaps of the bulk, there are edge states which propagate in a chiral way, which basically go around the bench only on one direction. They cannot go backwards. They are chiral. They only move in one direction. This is something which is well known from quantum Hall physics, but in synthetic dimensions, where one of the dimensions is that synthetic one, give very interesting new physics, which you can understand in comparing these two pictures. So this is a finite system in space, which is infinite in the synthetic dimension, which, by the way, differently from atoms, in photons can be made very large. You can have a lot of modes, while typically in atoms you have at most 20 spin states available. And you see, if you cut the system in the real dimension, the motion in the syntactic, in the motion on the edge will be in the syntactic dimension, which is a nice way to have a frequency converter. You shine red light on this side, you start getting blue light out of it. You send red light here, you get infrared light. You shine blue light, you get red. So this is a very simple way to get a frequency conversion for light waves. And it's a frequency conversion which is unidirectional, which is very different from shining light on a EOM, which creates symmetric bands. Here the bands are only on one side, which can be interesting for some applications. If you want to create an edge state which propagates in space, you can put an absorbing row of sides. So I have some sides which are basically non-existent. You're cutting the system in two. Then the chiral edge states go around and basically travel in space on the edge of this cut in frequency space. So they move laterally. So bluish light will move to the right. Reddish light will move to the left, which has no political connotation. You see, this is a funny way to manipulate light, you having another dimension. Imagine if you build an integrated circuit containing these features, you can have an integrated circuit which lives in 4 dimensions. And in 4 dimensions, you have many more ways of connecting the different sides. So it gives rise to a larger possibility for the connectivity of the device. Could be interesting, who knows, interesting possible way to develop applications. Experiment, again in collaboration with Philippe in Montreal, we try to realize an example of 2D model, and Harper-Hofstetter, for some technical reasons connected to the platform, is not the easiest thing to do. It's better to go Haldane, which is another model which has topology. It basically can be either hexagons or brick wall, doesn't change. It has a non-trivial topological number in some regions of the phase space. So we are aiming at realizing this model. Now, rather than building an array of many loops, each of which has one synthetic dimension, we realized a model which has 2 synthetic dimensions. And the idea, basically, is to use the same SSH chain to generate the bipartite lattice of Haldane, but also interacting some long-range hopping terms. So from one side to a side which is, say, 50 sides away. So if you put this 1D chain in a sort of snake configuration, having the long-distance hops is like having a second dimension. So if you have a very long system, and you not only hop close, but you hop from here to here to here to here, you can consider this brick put here next to the other, and it creates an effectively 2-dimensional geometry. So putting several frequencies is a way to generate 2-dimensional lattices. This was invented before us by Shan-Hui Fan and his friends. But what we did with Philippe, the first author, Alexandre, is a brilliant PhD student, we implemented it together with the idea of SSH. So in this way, one has a bipartite unit cell, which is repeated in a 2D lattice. For suitable parameters, one can induce an effective time reversal breaking in the physics of the system, which is essential to get Haldane, and this is done by some circulator elements which create some mismatch in the light going in one direction and in the other one, otherwise it doesn't work. That was the critical advantage that we managed to implement in this experiment. And this creates the 2D Haldane model. How to see that we really have the Haldane model? That's an experiment for the band dispersion. This looks completely crazy band dispersion, but that's basically just because the way the dispersion is measured in this higher dimensional synthetic dimension is that one measures in this way, making some cuts, which moves slowly in one direction and fast in the other one. So these fast oscillations are each time one goes through the Brillouin zone on one direction, and then the slow motion is in this one. It's a technical problem which allows to reconstruct the band dispersion. We have here the band dispersion, which say this is graphene, where the Haldane has no gap, so it has Dirac points, and indeed here you see the 2 Dirac points. Then changing the parameters, one can go to HBN, which is a graphene where the two elements of the unit cell have a different energy. It's a configuration which is interesting, but is not topological. Or to the case where one has really Haldane. From the band dispersion, you see no difference between these two cases. But if you measure the Berry curvature, you see that in HBN, the two Dirac points here have opposite Berry curvatures. It's not easy to see, but this is red and this is blue. So the total chair number sums up to 0, while in the case of Haldane, you see here the 2 points are red or blue, depending on the sign. This is a smoking gun of the topology. Another way of seeing the topology is that the relative function, the block function within the unit cell covers the whole block sphere in the topological case. It has to cover all. Basically, the topology is some topological index of the mapping from the Brillouin zone to the sphere. So if it covers all the sphere with a given direction, it has some topological index. If it covers it in the opposite direction, it has 0 index. If it does not cover the whole sphere, there is no way that topological index is 0. That's a mathematical property of this mapping. It's a family of homotopies. It's a very geometric way of understanding. And this was done in the experiment. They measured this homotopy, and they measured the Berry curvature, which perfectly matches with the theoretical expectations. So now let's do physics with it. What is the most important smoking guns of the topology in the bulk is the integer quantum Hall effect. What is the Hall effect? Basically, you push electrons in one direction. They don't move there, but they move sideways. The Hall conductivity is 0 in the longitudinal direction. It's quantized in the transverse direction. So how to do this in photons? One cannot put the system at thermal equilibrium and measure the transverse conductivity, because photons are driven dissipative. But Tomoki proposed a way to do this in the context of non-equilibrium systems. One drives a single site. If a force is present in the vertical direction, the intensity distribution is not localized symmetrical around this point, but flows sideways with a displacement which is proportional to the churn, but is also proportional to the 1 over the loss rate. This is physically understandable. The photons only live for a finite time, so you push them, they will move sideways for an amount of space which is proportional to the time they stay in the system. So in these photonic systems, the transverse conductivity is not really quantized. It's quantized only modulo some non-universal quantity, which makes it a bit more difficult to assess, especially the measurement of the Chern number is based on a quantitative assessment of many things, including this gamma loss, which can be a bit complicated. Doing all the calibration in the best way we could, we find a Chern number which is actually in a surprising agreement with expectations by a few 10%. Say this is 10%, this is even better. Typically 10%, which is incredibly good. Here, this curve is the displacement as a function of the laser frequency, the frequency at which one is shining the light. And this probes basically the distribution of the Berry curvature in the different regions of the Brillouin zone. By integrating over the whole Brillouin zone, one reconstructs the Chern number. And he showed that the lowest band has a positive Berry curvature, which is a precursor of having a positive Chern number. The upper band has the opposite sign. These are all the signatures that one would expect for the Haldane model. Lower band, Chern number 1, upper band, Chern number -1. Same experiment with a graphene-like lattice, basically no effect. Basically because the positive curvature at the one Dirac point compensates with the negative one at the other one. So basically one gets no displacement. So this is an experiment which shows how the topology, how the Chern number affects properties in the bulk of a photonic lattice, which complements what has been done since the old works by Haldane, Ragu, and the MIT people on the edge states of photonic systems, where the chiral propagation on the edge was the first smoking gun which was observed in the earliest experiments in topological photonics, but the bulk was studied much less. This is an example of physics. Of course, physicists are always hungry, want to make a step further. What happens in 4D? The same experiment about the displacement is still possible, but now the displacement contains a part which corresponds to the first Chern number, but there are also other effects where several synthetic electric and additional synthetic magnetic fields are present, where the current also contains a term which depends on nu2, which is the second Chern number, which is the new topological invariant which enters into the game at 4 dimensions or above. So these were simulations done by Tomoki about the displacement of the cloud, exactly like those ones done in 4D. And they show that there is a displacement, a lateral displacement, which goes exactly according to this formula, which would be the way to measure in a 4-dimensional system the second Chern number. This is the form of the second Chern number as a function of the Berry curvature. The Berry curvature is an effective magnetic field, and in 4 dimensions it has more components, just because it's 4D. You have more possible entries in the magnetic field matrix. In reality, just side marks, the vector field is, the magnetic field is a vector only in 3D. That's a coincidence of 3D, because antisymmetric tensors are isomorphic to vectors. In 4D, this is no longer the case. So the magnetic field in reality is described by an antisymmetric tensor, which is an object with, it's a 4x4 object, antisymmetric. It's a much more complicated object, and this is an example of topological index of this object. I apologize, I have no intuitive understanding of this in 4D. From our point of view of condensation, this is very interesting because it allows to study condensation effects in higher dimensions. This is extremely exciting from the theoretical point of view. would be condensation in 4D, never done before. What is the KPZ physics in 4D? That's something that I learned at a recent school on KPZ physics in Les Houches. That is a very interesting topic. It has new properties. It has another transition, what I learned it's called the roughening transition, which happens at high enough dimensions. Basically, depending on the parameters of the system, one goes from a regime where the Bogoliubov excitations don't interact to a regime where the Bogoliubov excitations interact. And this reflects on the coherence properties. It would be very interesting to study. It would be a new way to generate mode-locked lasers. And one may also think that these systems will be much more robust against fluctuations. Typically in high D, the long wavelength contribution to noise, to fluctuations, is less important, just by phase space arguments. So one could expect that lasers in 4D would be much more stable. And as it was realized first in the group of Moti-Segev, this synthetic dimension lasing is closely connected to active mode locking physics. So it could be a way to generate new families of mode-locked lasers. All these are very interesting, exciting new developments. But in the last part of this the presentation, I would like to present something different, which is more related to Cargèse, especially to an activity that I would dream of being able to do, but unfortunately I'm not. So that's not a picture of me, if you had a doubt. You see, this wave is breaking. Wave breaking is one of the most exciting examples of nonlinear physics of waves. So when the wave is very long, very high, and gets to a spatial form of sea bottom, the wave can break, creating this sort of waterfall that surfers very much like to surf. What is a platform which could develop this kind of wave-breaking phenomena? It's a fractional integer or fractional quantum Hall system. So this system, this is just a standard Hall bar. You measure the longitudinal and transverse resistivity at spatial values of the magnetic field, such that the filling of the electron gas is fractional, is integer or fractional. You see that the longitudinal resistance drops to 0, and at the same time, the transverse resistivity in blue gets these plateaus. These plateaus are at very precise values, multiples of this resistivity quantum. And these are used for many purposes, including as secondary standards for metrology. There's a very interesting physics which was developed in electronic systems, in particular in transport experiments. In the last years, there's been a strong effort to do the same physics in gases of photons or of atoms. This is a pioneering experiment by John Simon. At the time he was at Chicago, who observed a baby fractional quantum Hall fluid of 2 photons. More recently, there's been an experiment somewhere in China of 3 photons. And this is an experiment done in the group of Marcus Greiner at Harvard, where the same physics has been done in a crowd of 2 atoms. So there is a lot of efforts in trying to push this research further to get to larger numbers of particles. So plenty of strategies are being built. Albert and I are working on something of this kind for atoms. So there is also from the experimental community a strong wish to go to larger systems. So in the next years, you could expect that something interesting will come from all these. What I will present today is something which is a bit platform independent, but looks at a property of these systems which is not the usual observable. It's something which is related to the new physics of the edge. Basically, the fact of the edge, that the edge can support modes which move on the edge, which is not now just a single particle physics, that's a many-body physics. So these are the edge modes of a many-body system. These are experiments which have been done on these systems, as shown a fractional charge being transported. They have seen some indirect evidence of fractional statistics. There's a group of Mike Manfra. Wonderful experiments in Paris about collisions of elementary excitations on the edge. This is Anion collider in the group of Gwendal Febvre and friends. These are experiments, however, which are based on transport. I'm more in this talk on collective modes, like sound modes, which are quite similar to the edge modes that people in BCs was used to study kind of 20 years ago. So you take a condensate, you shake it a bit, and you look how the edge responds to external perturbation. This is an experiment where this physics was studied in electronic systems. This is a group in Japan, Goyusa. Similar experiments are done also in the group of Gwendal. Basically, one excites the edge with some electrode, and then one uses some electric or optical detection to see the perturbation which is induced on the edge. The edge is just kind of sound waves on the edge of this electronic cloud. In the PhD thesis of Alberto, we studied this physics for a cloud of particles which are contact interacting. Basically, we took a circular cloud, we applied on it some potential, and we looked at the waves which are induced on the edge. This is a dipole, this is a quadrupole, an hexapole, octupole, all the kind of waves you can create on the edge. So as expected, you generate the perturbation, and these waves will start moving in a chiral way around the cloud. I've been working on this problem already for almost a decade, but what Alberto did in this was really the breakthrough. He invented, while being locked down during the COVID, he invented a new way to solve the many-body problem numerically. And this, his algorithm allows to go up to a number of particles which are of the order of 100. Basically, it was an order of magnitude with respect to all the previous calculations we had done. And this allows to make some theoretical experiments on the system. So we could do the numerics, but we had not really a clear idea what physics we could see, except that these waves will go around the system in a chiral way. So we did a numerical experiment. In the weak excitation at long wavelength, we recovered the prediction of a chiral-Luttinger liquid. Chao-Gang-Wen theory, chiral-Luttinger liquid, well known. You have a linear response proportional to the filling of the cloud. Everything is perfectly consistent. This relieved me that, and convinced that what Alberto was doing was correct, because finding a quantized transverse conductivity was not something completely trivial in this many-body setup. Then we started looking at shorter wavelengths or stronger perturbations. He really did all the experiments as a good experimentalist would do, with very precise scanning all parameters, and then one day he came out with this idea that all these numerical observations could be summarized by this Korteweg-de Vries equation for the time evolution of the perturbation on the edge. And this equation was written just by experimental tools. He did the experiment for numerical experiment for different parameters, and then he formulated the theory, and he checked that all the numerics was falling into this category. That was kind of amazing. Then browsing the literature, there were some theoretical works having proposed these additional terms from very abstract techniques of conformal field theories. So the PhD opponent of Alberto was Steve Simon, a guru of this stuff, and he got reasonably convinced that this was likely correct, and Alberto could get his PhD degree. Then the natural question is to see, can we see some wave-breaking phenomenon? Because that Korteweg-de Vries equation is one of the equations one studies to describe waves on the ocean. So we did some simulations and we realized that this was not happening. We could see some wave bending. You see this wave get a bit asymmetric on the front, which is what you see here. But you never see wave breaking. And basically the reason is that there are additional dispersion effects, the third derivative term in the KdV, and quantum effects which destroy the wave breaking. But is it still possible to see interesting nonlinear phenomena? And this was the project that Tanguy undertook during his stage in Trento. And we studied the response of one such object, one FQH cloud, to a potential with an electrode, which is here plotted in red, which is switched on for some time and then switched off. Solving the KdV equation, one finds that on the front there is a complicated shape which eventually evolves into a soliton plus something. On the back, it evolves in something which very much looks like a nonlinear shock wave. We still have to check, but if you look at it in the phase, it clearly tells you that this is a nonlinear shock wave. So we have to do all the fitting, but very, very possible. So this is a nice way to generate solitons, KdV solitons, around a quantum system. But these are not solitons of KdV you could have in water. These are solitons on a quantum system. So this opened a new way, the new window, to studying quantum solitons. So the experiment, which would be like this of Goyusa, we have to understand what are the exact parameters to generate the soliton, because we cannot calculate the parameters, the KdV parameters from scratch. We are not able, with something that we are trying to estimate from the system. The goal would be to see some quantum effects. And in the thesis of Francesco De Bortoli, there are many features related to these quantum properties of the soliton. So this would be a new window onto solitons in a completely new quantum framework. So other experiments. Yes, please.
How do you check if these are kind of, because if I put a reflective ball and I make them bounce, are they stable to my scattering?
Basically, if you put some disorder here, all this feature just typically goes around. There is nothing special that happens.
Can they propagate?
Basically, they only propagate in one direction. And one more thing is that if we put two such electrodes, one after another, and you tune the parameters in order to get two solitons with different speed, they basically cross each other, like it would happen in a standard KdV. You can ask Tanguy, he's there. He can show you some numerical simulations for the different cases. So they're really chiral objects which only go in one direction. Good. Here is a more elementary physics to be studied in this system, pumping only one mode, pumping only the second mode. One can see optical bistability, self-pulsing, or even some parametric down-conversion. The big question is, what is the nonlinearity in the experiments? The cavity modes have been observed. So to do the calculation, since with electrons we have troubled, we try to study with a cold atom system, Harper-Hofstadter with contact interacting bosons, where we can solve everything by standard exact diagonalization of three tensor networks. And we found a very interesting phenomenon, that the nonlinearity of these systems is extremely strong. So here you see the chiral edge modes. This is on the mode. And you see that already the mode with angular momentum 2 has a huge splitting by the conversion of one photon in the L equal 2 mode to a pair of photons of L equal 1 photons. And this is a sort of strong coupling between these two states, a sort of Biexidon-Feshbach blockade phenomenon in the language of nonlinear optics, where one can see that there is a very strong effective quantum blockade. And this is a quantum blockade not of light, but it's a quantum blockade of many body excitations on the edge on FQH cloud. So it can be a way to generate quantum states of the collective modes on the edge. It's a sort of quantum hydrodynamics of very complicated collective excitations of a fluid. You can get a single quantum, you can get a pair of quanta. Can it be useful for something? No idea, but it's conceptually very interesting. You build quantum hydrodynamics of extremely complicated underlying platform. With this, I'm at conclusions. I hope I've convinced you that this is an extremely exciting field where different fields basically touch each other and give rise to new questions. This is a list of interesting topics. But if you wish to know more, the best is to come and visit us in Trento. In summer, we have a lake. It's not the sea, but still it's interesting. This is some people of the BEC Center. And if you prefer to come in winter, or in fall, when there is the good wine and chestnuts, we are going to have a workshop next October on microwave quantum optics. So please feel free to apply to the workshop. If you want to read more, this is a sort of a few review papers on the topic where you can get inspiration. And I thank you for your attention.